Same floor. Okay.
Yeah, we'll be here.
Yeah. We discussed papers.
I could give a short warning, the senator have to take their phone.
All right, we're gonna start now. People online can hear us. It's my great pleasure to introduce you to Professor Marcio Catelan today. He's a full professor at Pontificia Universidad Catolica de Chile for like 10 years already, and more, a full professor, as a full professor, and you have been a professor there for like over 20 years, if I understand correctly. So he specializes in stellar populations, in the Milky Way, stellar evolution, globular clusters, you name it, so many things. Stellar variability. He has written books about it, and he's a very proficient author. He has also gotten several awards over the past 20 years, 30 years, including a Hubble Fellowship and an NRC Fellowship in the 90s. Also, Excellence Teaching Awards, and you have also supervised several dozen theses, master theses and PhD theses. Yeah, a book. So yeah, it's my pleasure to introduce you, and the floor is yours.
Thank you so much, Gustavo. Thank you all for being here, battling the snow to get to the building. That's it. I'm from Brazil, so this is a beautiful experience for me to see such a blizzard.
This is the biggest storm I think this year.
No kidding, right? There seems to be another one coming out this weekend, so I'm looking forward to it.
We have a sled if you want to go to Bergen.
Okay, that might be helpful. Okay, so I'm going to be talking about what we've learned from time result wide field photometric surveys. My talk is going to be based partly on a review talk and paper I published recently, so if you want to access that paper, some of the contents of this talk will be there, and you will be able to read it at the comfort of your offices and rooms and homes later on. Okay. So this is the variability tree that was put together by the Gaia team and released on occasion of the second data release. And I apologize for those of you who were at the TASTE seminar that already heard the same story, right? So this is a very complex tree. As you can see, it covers different types of variability, mostly stellar variability, but there's also some extragalactic over there, AGN, which is complex on its own. What I wanted to point out to you is that this amazing knowledge of different variability classes and subclasses that we've been able to build have been achieved, this is not working, thanks to variability surveys. There have been many variability surveys over the past several decades, some smaller, some bigger. Here I copy some of the logos of some of the bigger ones, and we've learned a tremendous amount of information from these variability surveys. I do want to point out to you that most of these variability surveys do not have actual stellar variability as their main focus. The focus is rather on other things like planetary transits, extragalactic supernova, which are distance indicators and very important for cosmological applications, microlensing events, which have been proposed to search for dark matter in aliens, right? I'm not the one to complain. I'm a stellar astrophysicist, and I definitely like the fact that we have all of this at our disposal to study stars, other types of stellar variability. Another main driver of these variability surveys has been the detection of potentially hazardous asteroids, planetary defense, right? Pan-STARRS, as an example, Pan-STARRS was largely funded by the United States Air Force. The funding came from the USAF, right? Most of it. So that comes to show that we, as stellar astronomers, can definitely benefit from the interest that these phenomena generate in the public and in the higher authorities alike. For most of my career, I've been studying pulsating stars. So pulsating stars in itself is a complex phenomenon that nowadays, with the amassing of all this information over the years, we have been able to decipher to a large extent and decouple into different instability strips across the HR diagram, different types of pulsations, radio, non-radio, P modes, G modes, solar-like, etc., and the mechanisms that excite them. So we started purely with taxonomy, and from taxonomy, slowly we fed our physical theories, and in this way, we started making sense out of the variability classes that have been empirically discovered early on. When we talk about the classical instability strip, there are many instability strips all over the place, as you can see here. We are talking about this band, this diagonal band here in this diagram, which covers classical Cepheids, type 2 Cepheids, Arliara stars, delta Scutis, and associated variables. In the pulsation tree, you see that it's actually this part here of this diagram. So this is the one that has generated so much interest on many accounts, including the fact that many of these variables are excellent distance indicators, and therefore they can be used to trace structure in the Milky Way and nearby galaxies, and also the expansion of the universe, in the case of the brighter variables like classical Cepheids. The number of variables that we've known has increased quite sharply starting in the early 1900s because of the invention of photographic plates and the fact that a large number of photographic plates started being amassed and analyzed. The story behind this is in the book I published with Forrest Smith, so you're invited to take a look if you want. So this is a linear scale, so the increase has been substantial, but still, if we think about nowadays when we are already at the level of 10 to the 6th and 10 to the 7th variables, the increase initially was quite modest. And it was modest because we had to rely on quite rudimentary methods to measure stellar variability in photographic plates, to measure stellar magnitudes in photographic plates. Henrietta Leavitt was a very important figure in that regard. I'm sure all of you have heard her name. She invented this nice little device, which is called a fly spanker, for obvious reasons. It looks like a fly spanker. It's basically a piece of plate, a photographic plate, on top of a metal handle, tiny one, that she could overlap on photographic plates for measurements of the magnitudes. So she could put on those tiny pieces of photographic plate stars of different magnitudes and the kind of brightness, kind of impression they would cause on the plate. And by overlapping this fly spanker on the plate, she could actually measure the brightness of the variables, and in this way also measure the variations in brightness of many of those variables.
Do you know what the precision of this is?
Well, it's not so great, right? But
Is it
yeah,
half?
not millimag for sure. It's,
I'm just curious.
yeah, it will probably be a tenth of the magnitude. She would never detect small amplitude variables. Later on, a more sophisticated approach came up. This is Lindsey Graham at a blink comparator. A blink comparator was a device that matched a couple of plates of the same field and blinked them in quick succession so that one could see from the eyepiece, the trained user of the machine, objects that actually changed brightness from one plate to the other. And in this way, many variable stars could be detected and measured as well. Yes.
I just want to highlight, I was at Yerkes Observatory, so it's one of those, that old ones, the largest refractor in the world is
Right,
Yerkes.
yes, absolutely.
I saw exactly that machine
Okay.
there, and anyone for, I mean, I paid $40 for admission to see the tour, but anyone want to see that, you can
Right.
see these kind of things and see a supernova explosion by blinking two plates, actually in live still, if you
It's
ever
beautiful.
join a Yerkes Observatory trip.
Yeah, absolutely. So these were wonderful machines, and they helped a lot to go from this manual process to a semi-automated process. So it helped increase the number of known variables over time. And fortunately, in more recent years, people have recognized the importance of properly storing and scanning the photographic plates so that we could use nowadays the information from those plates that have been stored for over a century in many cases. Particularly, Dash at Harvard has been at work, or have been at work for several years doing this very systematically. The final data release that was put out was late December last year, and unfortunately the project is already closed. They had expected to have as many as 13 data releases, but of course budget shortages cut their project short, so they had to do it quickly, more quickly. So there are other efforts of this kind, for instance, in the UK. And this is very important. There is a lot of precious information in ancient data from the time of the photographic plates, that we can use and extract to study the properties of stars. And I'll show you some examples. So here's an application of the combination of early data as scanned by Dash with more modern data obtained with a variety of surveys. So we used such combination of data to study the long-term evolution of Cepheids. We used these data basically to measure the evolution of the stars across the HR diagram, which we cannot see directly by pinpointing the star's position over decades in the HR diagram itself, but we can probe by means of the period of the stars that are crossing the instability strip, and they are changing their properties, physical properties, as they do so. So the way we went about this is as follows. So this is the phased diagram for an LMC Cepheid with a period shown here of 20.32 days. And you can see that the phasing of all the combined data was not so great. There is a lot of dispersion in phase. And this dispersion in phase we can interpret as a sign that the star has not kept the same period always. The period of the star has changed over time on account of the fact that its physical properties have changed over time as it's crossing the HR diagram. We can measure this displacement. We can go backwards in time. As you can see here, we did this with the earlier data, separating the data in different chunks. And we could measure that. This is the observed minus computed position, the displacement, with respect to what we would have found if the period were exactly constant. The quadratic line that we get here is a clear indication of a period that is changing linearly with time. When we take that into account, the period that's changing, and try to rephase the light curve, we get a much better result. As you can see here, there is still some spread, vertical spread in particular, but that's not surprising because we are combining early photographic plates that were very sensitive in the blue with I-band data from Ogle and visual data, mostly in the R-band from Marcio, and Gaia data, ISIS data. So the changes are not surprising. But we are pretty confident that we measured a good period change rate for this star. So again, what does this mean? It means that we are tracing the evolution of the Cepheid as an intermediate mass star, as it is, as it crosses the instability strip on different occasions. A Cepheid is expected to cross the instability strip first as it goes along the Hertzsprung gap region, in the shell narrowing phase, towards the RGB, and then when it's already burning helium in the core, it undergoes these blue loops in such a way that it goes first to the left and then back to the right to the AGB. In each of these crosses, the structure of the star is changing, and as the period goes inversely with the square root of the mean density of the star is changing. In each of these crossings, we can predict the amount of period change that should be expected. So in the first crossing and the third crossing, as the star is decreasing its density, the period should be increasing, and vice versa in the second crossing where the period should be decreasing. We carried out this kind of analysis, as I showed you in the previous slide, for over 1,300 Cepheids in the LMC, the biggest sample ever in any galaxy, even the Milky Way, and compared with models that we computed with MESA for different assumptions regarding the rotation rate, initial rotation rate of the star, and the mass of the star. So the empirical points are shown in gray, and the models are shown with the different lines. So positive rates, meaning first and third crossing up here, second crossing, negative rates down here. And we can see that by and large, the models are pretty successful at matching the observations. And one especially interesting thing that pops up from this diagram that's not immediately obvious perhaps at first is the fact that we have a couple of stars up here. You can see that the third crossing region is well populated, as is the second crossing region, but the first crossing region is basically empty, as it should be. This is a Hertzsprung gap. It's a gap for a reason, right? Historically, it's a region that has not had a lot of stars observed in because it's a very fast evolutionary phase. It's a fast evolutionary phase, thus the period change rates are high. And we found here a couple of stars that are consistent with first crossing, so this is a nice finding. And their period change rates are very well measured, we believe, because the period change is so large that the impact on the light curve is so obvious that even just with OGO data, we are already able to measure very decent period changes. So we believe we've detected a couple of stars crossing the first, for the first time, the instability strip. They should have masses between 4 and 5 solar masses. So here in the HR diagram, if you look 4 and 5 solar masses, they should be crossing the instability strip around
I have a question.
Yes.
Maybe it's better to ask it now so you don't have to come back at the end of the talk. So this is for the LMC, right?
This is for the LMC.
And are there theoretical estimations of the number of stars that could be found in the first instability strip crossing for the mass of the LMC?
Right, we didn't do actual population synthesis here, right? So I wouldn't be able to answer your question until we did that kind of exercise. I can only tell you that the evolutionary time down here is at least a factor of 10 faster than in any of the other crossings. So we should observe a 10 or fewer first crossing stars. And indeed, we observe very few.
What's omega zero?
Hmm?
What's omega zero?
Right, these are the initial rotation rates that were assumed in the calculations. So we have non-rotating stars and we have fast rotating stars. The impact on the detailed evolution is rather subtle. It's not a major contributor, as it turns out. So these theoretical models that we use here are from MESA, that you all know and love, but we also have our own stellar evolution models, the so-called Princeton Goddard-Cook stellar evolution models. My PhD, former PhD student, Oliver Alcarci, was in charge of the latest updates, and we are just about to release the largest yet set of horizontal branch evolutionary tracks for low-mass stars. The code is especially tailored to study low-mass stars. And these are horizontal branch stars, so Outlier stars are on the horizontal branch, so these will be very useful for studying outlier stars in particular. Talking about which, I can show you here another example of this O-C technique being applied to an outlier star in this case. We've done it for many such outliers towards the galactic bulge. And here's a very nice example where you can see that the light curve is going back and forth, right, as time goes by. So we believe that what we are seeing here is the light travel time effect. Basically, we have an outlier star in a binary system, and the light from the outlier star takes longer to arrive at us when the outlier star is farthest from us in its orbit, and vice versa when it's closest. So in this way, we can actually model this phenomenon, and we can, from the O-C diagram, the same one I explained to you before, get this beautiful curve, model it in terms of orbital parameters of such a system, and from that infer for large numbers of outlier stars we've been studying, the distribution of mass functions that by assuming an outlier star typically with a 0.6 solar mass, we get also the distribution of companion masses. This is like population outlier mass studies, the first one ever. And we find that the companions appear to be distributed in 3 modes, mass-wise. So we have the higher mass companions, probably comprised of white dwarfs, perhaps some neutron stars as well could be there. We have this low mass mode, likely comprised of brown dwarfs, substellar objects. And we have this mode over here as well, which could be like M-type dwarf stars. Another thing that we can do with our outlier stars, just by taking their periods without worrying too much about where exactly they are located in the sky in terms of distances, is the Osterhof analysis. To assign an object to an Osterhof group, we have to compute the average period of the fundamental mode outlier stars, which are stars like this one. This is the fundamental mode outlier star, and plot them on a graph as a function of the metallicity. So these are galactic globular clusters. And you can see that when you make a plot like this, there are 2 main clumps, and there is a region in between that's largely devoid of globular clusters. However, when you look at globular clusters belonging to nearby dwarf spheroidal galaxies, and you look at the dwarf spheroidal galaxies themselves, what you see is like exactly the opposite. The region that was a gap in the previous diagram, right? Now it's filled with objects. And there are fewer objects in the Osterhof 1 and Osterhof 2 regions. So this difference in distribution between bona fide galactic globular clusters and extragalactic objects led me a few years ago to claim that the galactic halo could not have been assembled by the accretion of dwarf galaxies resembling present-day Milky Way galaxies. And by present-day Milky Way galaxies, I remind you that this was done in 2009. A lot has been learned since then. Many dwarf galaxies, ultra-faint dwarf galaxies and streams have been found since. The situation has become more complex for sure, but it still holds true that the standard dwarf galaxies like Fornax, Canis Major, if it is even a dwarf galaxy, Sagittarius even, that those kind of building blocks would have built a halo that would not look like this, right? It would be filled in the Osterhof gap region. Okay, back to our history of the increase in the number of stars over time, known stars over time. This is the same diagram, but now extending beyond 1980. This only reaches out to about 1980. So this goes beyond now 2000. up to before 2010. And now the scale is changed to a logarithmic scale, as you can see. Right? There is a change in slope. This change in slope has been brought about by the passage from photographic studies to CCD studies. That represented the birth of large surveys, large photometric surveys that used CCD cameras, which could be read electronically and processed by software that we all use and love to this day, like Dufo, Delo. So the discovery of the CCD led to the award of the Nobel Prize in Physics to Boyle and Smith. Their invention was in 1969, that's the year I was born, and the Nobel Prize came out in 2009. And indeed, the CCD represented an evolution, a revolution in our field. We can compare, the CCDs themselves have been evolving tremendously over time. We look at the earlier cameras, for instance, from the Ovaltine, and you see how they have progressed over time. Individual chips became larger, more pixels, and arrays could be put together, mosaics could be put together with many such CCDs to carry out wide field surveys of the sky. I have a table here showing the evolution of the OGO project in terms of camera size and other projects, other properties. You see that initially it was just 4 megapixel camera, just like what you have in your cell phone, right? Going all the way up to 256 megapixels. And this is where we are now with OGO. So it's much more powerful than it was early on. And eventually we got to build DEC, which I know several of you have used. And it's a very powerful camera with 62 CCDs. Now, 520 megapixels in total with a very nice resolution. And this, again, is what's responsible for this amazing rise in the number of known variable stars over time. Now, when we try to study the galactic disk and bulge, we are faced with a major problem, which is dust extinction. So you look in the visual and you see that the nuclear bulge, for instance, is largely hidden behind high columns of dust. You go to the near infrared, on the other hand, and you see that this tends to get, the stars tend to pop up just because in the near infrared, the amount of extinction is much reduced as compared to the visible. And this is why from Chile, we led the VVV survey and its extension, the VVV-X survey, which was a survey targeting the Milky Way bulge and central disk in multiple passbands with extensive coverage, time coverage in the K-band. The resolution was much superior than in the case of 2MASS, and also the depth, this being based on a 4-meter telescope. So this is the camera that we used. It's an amazing camera that was constructed by our British colleagues. The field of view was completely unprecedented compared with other near-infrared facilities that have been available. And we put this to good use to carry out the VVV survey, and other colleagues also used the same camera to do the time-resolved survey of the Magellanic Clouds. This is where the VISTA telescope is. This is Cerro Pachán. This is the VISTA telescope, and much to our regret, VIRCAM is now retired. At the VISTA telescope now is another camera. It's a foremost camera. It's a multi-object spectrograph built by ESO, and VIRCAM had to be taken out. It's a very special camera that was specially designed to work with this telescope, so it doesn't look like RIRCam will ever be used again, unfortunately. On the other hand, there is still the new firm camera available on the Blanco 4-meter telescope, 28 by 28 arc minutes, and we've started with Cheng Gu, who is now a professor at the University of Valparaiso, the Renew project that is using NUFER to continue the VVV coverage of the Milky Way inner disk. We hope to extend that to the bulge in the future. Looking to the future also, we are all highly expectant of the Roman Space Telescope that will have near-infrared capabilities. And going to the mid-infrared, we'll also have the Near Earth Object Surveyor, which will likely provide us with very useful mid-infrared data towards the galactic bulge in 2 band passes, very similar to WISE's W2, and like a blue version of WISE's W3. This will be out in a few years, we hope. All right, so going back to our history of the evolution of these surveys, I want to emphasize once again that this major increase in the number of detected variables was not only due to the technology of building CCDs, but also to our capability to extract the data, to read the data from the CCDs, and process them, and carry out photometry on those images. So we owe a big debt of gratitude to Peter Stetson and Paul Schechter in particular, who have been pioneers in this field. Another method that has been used very extensively in recent years is image subtraction, also called difference imaging. This is used in most surveys that attempt to provide alerts of objects that are varying brightness for follow-up. So this is from our ALERCI project. You can see here 3 examples. In the case of an RLR star, a YSO, and a Type 1a supernova. We always have to have a template image, and then we take a science image, we match the scene of the 2, and then we take the difference, and whatever is left should ideally be the variable object. In this case, an RLR star, in this case here, a YSO, in this case here, a supernova Type 1a in this nice galaxy. So where are we now? So this is an updated plot showing the number of variables as a function of time. And we are here. We just passed 10 to the 7th stars, and we are going up soon to 10 to the 8th. With LSST, the projected number of variables, we're talking now about hundreds of millions of variable objects to be detected with this magnificent facility that's been built, LSST CAM, with this amazing detector, which is the biggest camera ever built, and which will be in place, we hope, very soon. These are images from the laboratory using LSST CAM, and this is an image that was taken very recently with the commissioning camera, as LSST is undergoing commissioning. Commissioning went very well with the commissioning camera, and now commissioning will continue with LSST CAM. We're all looking forward very much.
So how is the relative proportion of galactic versus extragalactic variables evolving?
That's a very good point. My plots show only galactic variables, I have not kept track of extragalactic size. That's a good one. Right, so as I said, this is an image from the commissioning camera. LSST CAM will be up soon, and we hope the survey itself will start in the coming months as well. When it does, the amount of data that it will be amassing, we're talking about 15 terabytes per night, and a total number of detection of 37 times 10 to the 12. It dwarfs everything else comparison, and it will be done in 6 filters. So it's going to be a huge amount of very precious data that we want to study. Of course, this represents challenges. I was going to tell a joke here, but maybe not. One of the things that we want to do with the variables that we will be detecting, hopefully at large distances in the outskirts of the Milky Way and beyond, is the period luminosity relation. This is the period luminosity relation in Weiss and height index, which is a kind of magnitude that's built in such a way as to be reddening insensitive. So you can see different bands over here. You can see the classical Cepheids over here, very beautiful PR relation, originally discovered by Henrietta Leavitt. You can see up here the different sequences that are followed by red variables. This is the so-called Wood diagram part of the period luminosity diagram. And down here you can see Yara Lyrae stars in a more blobby kind of distribution. Alan Sandage was a pioneer in studying the absolute magnitudes of our Lyrae stars. He realized that they are not really correlated as much with period as they are with the metallicity, for reasons that we explained in the theoretical paper back in 2004. Very quickly, the horizontal branch is horizontal, individual, so the Yara Lyrae stars do not cover a wide range in luminosities, but it does cover a fairly wide range in temperature, and therefore, when you build a period luminosity diagram, you get something that's very spread in this direction, but not much of a spread in the vertical direction. Things improve considerably when you go to the near infrared, as you can see following this diagram in this way. In the near infrared, PR relations for our Lyrae stars are excellent. So we use that a lot to study our Lyrae stars and other types of variables, particularly in fields that are subject to high amounts of extinction. So one application is the study of of nearby structure in the outer halo. I had a student involved in this early on. I showed you this plot at the tasty seminar to show the level of complexity that we've reached now in study of nearby streams and structures, galactic archaeology. I pointed out to you as well that Orphan Tema were two different structures until using our Lyrae stars, Kopasov and Ting Li were able to show that the north and south part are actually connected. Gustavo Medina here is conducting a very nice survey of the outermost halo, searching for Lyrae stars, and he found some really far out in the outer halo, and using this, he was able also to put together a density profile for the galactic halo, finding, not surprisingly, a broken power law. And very nicely for what's coming up in the near future, he was also able to project the number of our Lyrae stars that should be expected at distances beyond a certain threshold in the halo. So his results are basically this gray band over here. We look at 200 kiloparsecs here. This is close to 1,000. So this means that beyond 200 kiloparsecs, we should still find around 1,000 our Lyrae stars or so. And so far, we've only found a handful because studies have been based on pencil beam analysis, like this other example here with the next generation Virgo survey. These are our Lyrae stars in the direction of the Virgo cluster. How are you doing?
Before we do RLI,
Yes.
quick question. Going back to this interesting thought you had with the different binary mass peaks.
Yes.
What fraction of the RLIs would have companions of those masses?
Yes, well, our estimate of the total number of Lyrae stars in binary systems is of order of 5 to 10%.
And
So it's a small fraction.
and each of those peaks were roughly 130.
They were about, yes, exactly. The one with a higher mass companionship was a little higher.
It was surprising because we know about brown dwarf desert. It
Yes,
should not be brown dwarf companions at those periods. So I guess get back to Chris's question, what are they? Should they be brown dwarf or should they be something else?
I don't know, it's not really.
Are they the
it's
long
not-
secondary period? The different?
Well, we don't see those stars. All we see is this gravitational pull back and forth that's reflected upon the Omenasy diagram because of the light travel time effect.
It's
So
different.
we can only infer a mass by assuming a mass for the RLI star, and we get these masses. Now, how these systems are actually built and what's their survivability, I don't know.
Because I was on Brand's types, not Brand's.
No, I know, but the long secondary periods are also, well, okay, they're more research.
Right, yeah, no, long secondary periods are for very bright red giants. This is.
Are they
not the
similar
case.
periods, I guess, in the end they have to evolve, I think it's a.
Yeah, they do have to evolve, and this is actually a problem, and this is one reason why binary stars containing RLR stars seem to be so rare.
The
If you look,
post-giant stars.
right, exactly, they're post-giant stars. And what happens is that if you don't fine-tune the system well enough, what will happen is mass transfer, and what would be an RLI star quickly becomes an extreme horizontal. That's the so-called blue subdwarfs. The blue subdwarfs are produced exactly in this way, right? They are like failed RLI systems.
What many periods do these binary RLRs have? Is it a wide range or?
The orbital periods?
Yes.
Oh, they're very long always. We're talking about thousands of days. So
So they
since they're fairly wide orbits.
roughly expect they avoided a compound.
Correct. Exactly. Yeah, they should have survived those expansion phases.
Except the mass is surprising, companion mass is surprising.
Right. I'd be interested in hearing more from you. It's not my field, brown dwarfs.
It's a long-standing puzzle.
Okay. Okay, thank you. All right, so we can also analyze the distribution of Cepheids on the galactic disk. This is the result from a variety of the face-on view of the Milky Way disk based on a variety of optical surveys, and this is a picture that was put together recently using OGO data. And one thing that's interesting here, these are only classical Cepheids, is that depending on the age of the Cepheids, the distribution is actually different. So it's like the Cepheids are tracing the moving of the spiral pattern over time, so that younger Cepheids are located here, older Cepheids are located further out. So they appear to trace different regions of the spiral arms. In the visible, however, you cannot do much in terms of studying spiral arms or anything close to the galactic plane, so we go to the near infrared, and in the near infrared, we've done quite a bit of work from Chile, trying to find Cepheids on the other side of the galactic bulge from us, the first and fourth quadrants. We found quite a few, and in this way, we were able to put together a picture in which these Cepheids may be tracing spiral structure on the other side. Of course, we still need much more extensive studies to have a larger sample of well-studied Cepheids, cover a wide range of ages, so that we can fill this diagram even more. One other thing that came out of these studies is that the disk is warped, as you probably know. The OGO team had already shown this using the optical data at their disposal, so nothing reaching much out towards the regions beyond the galactic bulge. With VVV, my student Gerbe Hoydo, we were able to show the warping also in regions that were severely extincted, and we can see that depending on the position angle, the degree of the warping is different, as was also found in the visual in other regions. Gerbe also showed that there is flaring of the galactic disk, in the sense that in the outer regions of the disk has a higher scale height, and it appears to be correlated with age. As far as our Lyrae stars go, the situation is different. Our Lyrae stars fall like a triaxial ellipsoid, and so do the type 2 Cepheids, which even though they're called Cepheids, they're actually completely different in terms of evolutionary history from the classical Cepheids, as they are very low mass stars. They have masses that are even lower than our Lyrae star masses, so they're ancient objects as well. So it's not surprising that we found the Lyrae stars and the type 2 Cepheids pretty much to partake the same spatial distribution. Cepheids, again, were instrumental in showing that these are the Magellanic Clouds, that the small Magellanic Cloud is actually very extended along the line of sight. So the point of this cigar is pointing towards us, and this depth along the line of sight was well traced by Cepheids as well. Okay, I had some things to tell you about the properties of our Lyrae stars as we start digging deeper. I want to show you quickly that we've been able, thanks to these variability surveys that have extended over long periods of time, that variable stars we see in the sky, they're changing over time as well. Again, we see that not only because their periods are changing, but also because their pulsation modes may be changing. Here's an example of an Lyrae star that used to be a double mode Lyrae star pulsating simultaneously in the fundamental mode and in the first overtone, and then like 10 years later, it was a beautiful fundamental mode Lyrae star. Again, the stars are crossing the instability strip. It's very hard to see that happening just by measuring magnitude and color, but the pulsation that's present in some of these stars, the pulsating stars, are precious in indicating to us that these stars are evolving all the time. Okay, I think this was a big jump. Right, so one thing that we can do if we have not only photometry, but we also have spectroscopy and astrometry, is to compute orbits of stars. And if we compute orbits of stars, we're able to put stars in families. We're able to make sense of their origin in terms of the galactic formation. So this is a very nice recent study by Valentina Dorazzi et al., where for our Lyrae stars, they were able to compute orbits and assign different our Lyrae stars to different fragments that have been under study recently as contributing to the formation of the Milky Way. With this kind of information, you can also have metallicity distribution functions. I have a former student and one student working on this topic. I wanted to tell you that narrowband photometry may also be useful. Right? This is a beautiful paper by Vinicius Blanco and colleagues, 2021, using S+. So they took narrowband and wideband photometry for a star in the halo that turned out to be, from their analysis, a very good candidate for a very metal-poor star with alpha range of about -4. And they took spectra with Gemini, and they were able to confirm that indeed this is an extremely metal-poor star. And the beauty of narrowband photometry is that you can do this at a lower cost because some of the filters are well positioned so as to measure some features that are sensitive to metallicity. This is being exploited by different surveys. I have, again, a former student and a current student working on that. We just put out a paper using S+ with physical parameters and chemical compositions for a very large number of stars that were observed by S+. There's also the Pristine survey, etc. So I guess I'm running short of time, so maybe I was going to tell you about the efforts we are doing in Chile as far as processing data that's going to be coming out from LSST. We have an alert broker in place in Chile. It's one of the official alert brokers of the LSST project. And these brokers basically process the alerts that come out from LSST, and they try to classify those alerts into variability classes and their astrophysical properties. So Alerce is the national tree of Chile. That's where this comes from. The taxonomy is relatively simple so far. We are going to improve it in the future. We're using different types of machine learning techniques to process the alerts, currently from ZTF, but very soon, and Atlas, we've done some work there as well, but soon, hopefully, LSST and also LS4 we plan to process. We also have an anomaly detector in place, and if you're interested, you can go to the Alerce Explorer. There's this nice web page where you can search for stars, variable objects of different types, from kilosous to supernovae to pulsating stars, like here our Alaris star, retrieve the light curves, carry out the analysis, get their periods, and you name it. So feel free to explore that if you well, I have a lot more that I could show, but I think I'll stop here. So thank you very much for your attention.
Thank you for the nice talk. I guess we don't have much time for a lot of questions, but maybe we can have one or two short questions, and then we can continue the discussions in lounge upstairs. So are there any?
So the halo RRYs, they're thought mainly to come from disassembled core companions. And so what range of metallicity are they covering?
Right, so the metallicity distribution function of halo RLR stars is quite broad. It ranges from about -0.8 at the metal rich end, all the way down to -2.4 or so at the metal poor end. So it's very broad, and the peak is at around that field range -1. You go to the bulge, for instance, and you analyze the metallicity distribution function, and you find that it's very sharply peaked at a metallicity of about -1. So clearly there is a difference. Now, very recently, a group of metal-rich RLR star has been found as well. That's actually on the disk. They have disk orbits, right? And there's a big debate going on right now on the age of these RLR stars and how they came to have orbits.
So
they're plain.
but this then leads to the next question, which is that better statistics of the halo RLRs can then combine kinematics with metallicity to begin to say, okay, there was some companion of a certain mass that contributed one population.
That's absolutely something that we want to do.
Yeah. So that's now become feasible with LSD or
Well, absolutely. In terms of the photometry, we're going to go very far out. In terms of the spectroscopy, it's a different matter because we can go as far. However, we have these beautiful multiplexing capabilities that are coming online, part of the blue scheme, for instance. And in this way, we will be able to measure a lot of our live stars. And combining that with Gaia, GF4 is coming out, and we'll have a lot of data, time series, time result data for parallelity and other variables as well in Gaia GF4. We will be able to do a more comprehensive view, if not all the way to the outermost halo, because that's very challenging spectroscopically, at least for the inner end.
Otherwise, just a reminder that Marcio will be at the AB 103 office in the AV building in case you want to talk with him. You can also drop him an email. And yeah, if you're interested in continuing the discussions, we can go on. So let's thank Marcio again.
Thank you.
Thanks for the talk.
Forty-five is just
Yeah, but this was line, like 3 lines, we have 1 line for calculus.
Bueno, también un poco el formato de como que le
How hard it is to have a calculus. And then